So moving on, continuing through our little survey here of visualization, a slide to introduce a little bit about me. I am an astrophysicist at heart and by training. Here I am at the Green Bank Radio Telescope in West Virginia, my senior year of undergrad, and I came to this realm and came to this world by discovering that I need to visualize and analyze my astronomical data. And I pivoted my career between college and grad school to say, I love data visualization, I love statistics, I love visual analytics, I want to do more of this. So then I moved on and ended up doing computational and applied physics, have a strong interest in fluid dynamics simulations, but then that still wasn't enough data science and visualization for me. So I went ahead and moved on to doing a PhD, and somehow by the end, I was a computer scientist and went on to do a postdoc, and now I'm faculty at Northeastern University. I always like to amend my timeline here, say I wasn't just exploring visualization in computer graphics. I also got married, and being at MIT is sentimental. My husband and I met on campus here through mutual friends, and we're now the proud parents of a baby girl. But let's back up to that point there, and that's where I discovered visualization and how much I loved it. And here's one of my projects. I made this with Tracy Delaney, who at the time was at MIT, and Tracy had 8 years of gorgeous data from Spitzer and Chandra and ground-based telescopes, and she had no idea how to put it all together. It wasn't all spatial, they were different projection systems, they weren't aligned properly, and this is the final draft version that I made with her. And this is the Cassiopeia, a supernova remnant. It's about 330 years old, one of the youngest in our galaxy. I lovingly call this visualization the Hollywood version of her data. This was the press release version of her visualization. This is the first draft I made for her. And this is where I got that magical aha moment from her, where she saw her data for the first time and couldn't believe it, and saw that there were two shells in the expansion of this supernova, and they weren't perfectly symmetrical, and the jets were coming out. But little did Tracy realize that the visualization tool I used to make this for her was called 3D Slicer, and it was developed for doing surgical planning at Brigham and Women's Hospital. So I've spent the past 10 years working across disciplines. I've worked with physicists and chemists and medical experts in cardiology, neurology, and working also with cognitive psychologists to try and better understand at a low level how we in general see and perceive visualizations, and then trickle that back up to decision support systems for doctors or new visualization tools for scientists to explore their data. Now, I obviously don't have time to go through all of these projects today. Some of these, I take a tool or technique or visual encoding in one domain and take it to another one, and vice versa. But the most powerful ones, in my opinion, are when I am lucky enough to find sort of an empty spot, something that both or multiple communities need. Now, here's some of the doctors I work with cardiology. These are 3D renderings of arteries. So you have your heart, and these are the arteries that wrap around. And the doctors like the 3D rendering here for surgical planning, stent insertion, bypass surgery. But they also need to look at 2D, sort of the raw CT or X-ray data from their patients. They also need to look at data abstractions. So in this case, a tree diagram that helps them see where there are blockages. And they also look at other sort of statistical plots. In this case, it's heart function. So although each one of these has a good sort of specific task and purpose, they really want to look at all of these together to make a true diagnosis and exploration of the patient. Guess what? Astrophysicists have the exact same scenario where they have 3D, and I should actually say 4D, this could be time, volume visualizations, their 2D images, and all their data abstractions. And this is a very general sort of paradigm in the imaging sciences where the scientist or the doctor needs to analyze their data across all of these. Now, one of the key visual exploration functions for this is brushing and linking, where, as I highlight here in red, you want to select voxels or pixels in one plot and have it mark all over in the others. And this gets really, really tricky with the data management on the back end. I holistically call this gluing. You have to glue the data together before you can do your brushing and linking. This gets hard when it's from different telescopes, and you have different projection systems, and each one of these has different variables or derived variables, and it's not like having just a spreadsheet with the same, one set of columns. You have to have a more sophisticated way of dealing with this. So this was a long set goal of my astronomy and my doctor friends to say, can we build this? And here is now this was the prototype, and now it's a full-fledged piece of software tool called Glue. And this is a collaboration among myself, Professor Alyssa Goodman at Harvard, as well as astrophysicists Tom Robitaille and Chris Beaumont. And the whole goal was to make a visualization tool that was capable of dealing with multidimensional data and let you brush and link. And you can deal with gigapixel images and brushing across the different plots, and it's smart enough to connect everything for you. And we're excited to be the official visual analytics toolkit for the James Webb Space Telescope, which will be launching in about 2 years. And even though, here's another astronomy example, this was built for astronomers, this was fundamentally interdisciplinary from the get-go, and we engineered it at the lowest level to take into account different types of data and do 3D selection and make it really easy for scientists to write their own I/O plugins and customize it. Here's an example with some of our doctors working on the project for doing decision support system for brain tumor diagnostics. And if GUIs aren't your thing, we have an IPython terminal window. And it's fantastic because everything in the GUI, you can write the code and it will live update for you. And it's wonderful for reproducibility, scripting, and also because it's in Python, it can really easily integrate with other systems you might have or other code in Python. And with that, I'll put some information on the slide and move on to our next talk. Thank you.